What I'm going to do is to give you an overview of essentially the creation of billion-dollar markets in information technology in the past. This is a chart from a National Academy of Sciences report done in 2003, which is in fact the successor to some work done in 1995. I participated in both of these studies. And here's what it shows. It shows 19 different $1 billion subsectors of the information technology industry. So I can barely read them from here, but it says, RAID arrays, portable communication, the web, speech, broadband last mile, data mining, relational and parallel databases, the internet, local area networks, workstations, graphics, those sorts of things. Okay, so you can put the names of companies behind those. Okay, and for each one, what it shows, we should have color-coded this, but we began this in the black and white days. It shows university research, industry research, product introduction, and billion-dollar market. Okay, and there's a little key down at the bottom. The first version of this in 1995 got the moniker the tire tracks diagram because it looks like some Yahoo had driven across the page. Okay, so for each of these 19 categories, the thin line at the top is university research. The next horizontal line is industry research. The dashed line, the block line, is product introduction, and the sort of fat line off to the lower right is billion-dollar business. Okay, so that's when it became a billion-dollar subsector. It shows a lot of flows among the subsectors, and I'll talk about some of these in detail later on. And it shows a subset of the contributors in each subsector just for concreteness. Okay, and this is available on the National Academy of Press website, or the PDFs on the web I've pointed you to are pretty reasonable. So that's the general idea, and that's what we're going to talk about, how this happened and what conclusions you can draw. This is just sort of a fatter picture of one of these for a subset of the chart: entertainment, internet, local area networks, workstations, and GUIs. You see that the internet, there's ARPANET, Aloha Net, the internet itself, the Park Universal Packet is an example of industry research, product introduction, DECnet, TCP/IP by a bunch of vendors. There was also, SNA and LAN-MAN and a set of other brain-dead networking architectures that various vendors tried to shove down our throats. Workstations, Lisp machine at MIT and machines at Stanford. The Xerox Alto was a predecessor of those. The Xerox Star, the Apollo, the Sun were commercial product introductions, and clearly it's a multi-billion-dollar market now. So you get the idea. Okay, that's what's going on. I already said all of this, and here are the concepts that this illustrates. And to some extent, what we're talking about today is, can we accelerate this transition from idea to billion-dollar industry? And I'm honestly not sure that I'm optimistic about it. Okay, so I'm going to begin on a bit of a downer, but I think it's a really important challenge to see if we can do better. The truth is that over history in this field, it's tended to take a long time to assemble billion-dollar industries from innovations. On the other hand, there are lots of innovations in the storehouse, and if we can figure out how to move those innovations into market faster, then that's a significant contribution. Here's what this shows. Every major billion-dollar subsector shows the stamp of federal research, but it's really this complex interplay of universities, industry, and government that makes it happen. It's not a pipeline. There's lots of back and forth, and that's really important. There's this notion that you go from pure research to applied research to product development, and it doesn't work like that. It's a very complicated web. It typically takes 10 to 15 years from idea to billion-dollar business. And this has happened again and again and again. Can we accelerate that in some way? I don't know. But the track record is it does take that amount of time. There are tons of interactions. Here are some concepts that aren't directly illustrated but are elaborated in the Academy's studies that these pictures are drawn from. Unanticipated results are often as important as the anticipated results. I'll give you some examples of this later. It's hard to predict the next big hit. And I'll give you a specific example of that. What research does is put ideas in the storehouse that later on get assembled into products that people want to buy. Okay, so it's a complicated path. In biotech, it's easier to follow because you get a patent, and the patent is good for 17 years, and people license the patent. In IT, following the path is a little more difficult. University and industry research tend to be complementary, and visionary program managers have made a big difference. I'll give you specific examples of all of these things. Okay? And we can talk informally or in a question period after this about specific examples. So let me give you a few examples. And you're all familiar with the internet, but it's just important to realize Bob Kahn and Vint Cerf just got the Turing Award for TCP/IP. And that work began 7 years into the internet. And in some sense, the research was concluded in the middle 1970s, and the full deployment was in 1983. Okay, so it's a long and tortuous path, and it's just worth reminding yourself of this. So in '66, that was the first experiments in digital packet switching. And what's really interesting about this is at the time that ARPA issued a request for quotations to build the IMPs, the Internet Message Processors, around which the original ARPANET was based, the phone company said this was a waste of money. Nobody would care. Why would you want to do anything except circuit switching? Okay, and ARPA went off and did this. In 1969, ARPANET was inaugurated with 4 hosts. The first message on the ARPANET was not as dramatic as, Watson, come here, or anything like that. It was LO. Kleinrock's programmer was trying to log into a remote machine, but the IMP crashed partway through it, and that was as far as it got. So it was the first few words of login, was the first message successfully transmitted over the ARPANET. This is from Charlie's log on Len Kleinrock's website. Talk to SRI host to host at 10:30 p.m. on 29th of October, 1969. In 1975, okay, so this is now 8 years later, hey, there's 100 hosts. 1977 was the first time that internetworking was demonstrated. Internetworking routes packets from network to network to network. So this was some folks driving on 101 in the Bay Area in a truck, sending packets via radio to the Xerox Palo Alto Research Center, which went via ARPANET to the East Coast, which went by a satellite network to England. Okay, so ARPANET, as deployed terrestrially in the US at that time, was a single network. Right? Okay, so there are a bunch of links, and there are a bunch of IMPs, and there are a bunch of computers plugged into IMPs. We weren't using local area networks, and there was no routing from network to network. 1980 is when TCP/IP's design was completed. And 1983 is when the internet converted to TCP/IP, and that was a big, horrible day in 1983 in which the University of Washington and the other sites, but notice there were only 500 hosts, and that doesn't mean 500 sites. We had probably 4 or 5 hosts plugged into our IMP here, and everybody had that. Not local area networks, but the hosts were plugged into the IMPs. Okay, so there were a couple hundred people who got together and said, okay, this morning we're going to do it. And the whole protocol suite on the ARPANET changed. Imagine doing that now. We're a prisoner of our success. We can't conduct experiments on the internet today because you can't just goof around with this thing. People kind of rely on it. 1988, ARPANET became the National Science Foundation network, and there were around 100,000 hosts. That's only 17 years ago, 100,000 hosts. 89, CNRI, Bob Kahn's outfit in Virginia, connected MCI mail to the internet. Okay, so again, for those of you who are my age, you remember this, but for those of you who are students, you don't. It used to be that the public had email, but it was like MCI mail or something like that. And MCI mail was a big time-sharing system in Virginia or someplace like that, okay? And if you were an MCI mail customer, then you could exchange email exactly with other people who were on MCI mail, who had email accounts on that same time-sharing service. It was, the epitome of friends and family. Okay? And if you had friends who were on AOL mail or something like that, send them a postcard, sorry. Okay? Backbone speed increased. 1992, NCSA Mosaic, the first graphical web browser. And in 1995, became fully commercialized at 45 million bits per second. Let me say that in 1980, by the way, the backbone speed of the internet was 56 kilobits. Okay, so the speed of the modem that gets you really upset these days. Okay, so that was the speed of the ARPANET, the internet backbone, 25 years ago. Okay, 6 million hosts in 95. So, like everything else, exponential growth. Now, Cerf and Kahn got the Turing Award just this past June in San Francisco for TCP/IP, But it's important to realize that that was just one piece of what made the internet possible. So, for example, if you're one of the people who invented packet switching, okay, you're probably, you admire Vint and Bob enormously, but you're a little upset that folks don't actually care about the underlying technology that carries the bits. You might also be one of the people who did the internetworking work at the Xerox Palo Alto Research Center before TCP/IP came along. All right? And what happened there was Xerox tried in some sense to bottle this up. Okay? And Cerf and Kahn invented TCP/IP, their version of internetworking, and then, as I'll show you in a minute, in a set of very, very innovative ways, made sure that it became disseminated and widely adopted. We'll see how that happened in a sec. Okay, so Vint and Bob architected TCP/IP and achieved its dissemination and changed the world. But it was not the first internet working protocol, nor is it the only element of what we think of as the internet today. So again, here's just the picture. This diagram lists the Aloha Network among internets because Aloha was a broadcast network connecting the Hawaiian Islands in the 1960s. And the failure of Aloha, the collapse of Aloha under load, is what led Bob Metcalfe to envision the binary exponential backoff protocol that became Ethernet. So in addition to being a wide area networking protocol, the Aloha Network protocol inspired Ethernet, the ubiquitous networking protocol today, although the Ethernet that we use today has little to do with the Ethernet as designed and implemented back then. It's a sort of same name, largely different technology. Again, we were experimenting in the 70s with ring networks. IBM was big into token rings. There were all kinds of alternative networking technologies, lots of different protocols. Every company had its own proprietary network protocol. It was not so long ago that an organization called the State Department of Information Services here in Washington State attempted to mandate SNA, IBM's particular networking protocol, as the standard for all state agencies in the state of Washington, which includes the University of Washington. Okay, if you're a research university in the 1980s, it's bad for your health to be told that you can only run SNA, and that's what state government was trying to do. Okay, but it would have been ultimately bad for the state government's health as well. Europe standardized on X25, a different protocol. So why is it that TCP/IP became ubiquitous and drove all these changes? So here's what this illustrates, okay, from those points I made. This illustrates the stamp of federal research funding. Okay, it's sort of woven throughout, and I'll illustrate this more clearly in a minute. Shows this interplay between university and industry. BBN built the IMPs, for example. Okay, Cerf was, Kleinrock was a faculty member at UCLA. Cerf was a grad student at Stanford and UCLA. It's not a pipeline. 10 or 15 years from idea to billion-dollar industry. Okay, I want to talk a little bit about ideas in the storehouse. E-commerce. I don't think federally funded university research created e-commerce companies, but it played an important role in the internet, in web browsers, in public key cryptography for secure credit card transactions, in databases, in search, right? And the business challenge is to assemble those things into stuff that people want to buy. So Skype is in the news today, $2.6 billion by acquisition by eBay. Independent of whether that's a reasonable price or not, where did Skype come from?
Voice over IP.
Okay, so voice over IP, and where's voice over IP come from? Can you trace that back a little? Do you remember some early voice over IP systems? Okay, so CUCME is probably close to 10 years old, right? You remember these are these little ball cameras that were, at least for my kids, they were like an international flirting service in the evenings, okay? But yeah, maybe latter part of the 1990s, so 8 or 9 years old. Can anyone think of one before that?
Vic and Vat, SDR.
Okay, Vic and Vat. In the middle 1980s, Xerox had a thing called the Ether phone that ran at Xerox PARC. Okay, so the Ether phone is solidly 20 years old. There are a bunch of research papers describing it. They had servers that archived the voice and things like this, okay? So people on their desks at Xerox had voice over IP. It was pretty crufty, but in the middle 1980s. So voice over IP goes back a very long way. What's another important component of Skype?
Peer-to-peer.
Peer-to-peer. All right? And peer-to-peer also goes back a pretty long way, although not as far. All right? But certainly the focus in voice over IP as done by Cisco or various people like that is replace or interface with your PBX. All right? That is, it was an enterprise application which has been pretty slow in climbing the way up, partly because it cost a fair amount of money, partly because you were expecting it to provide the quality and reliability that your analog phone had been providing or digital phone had been provided. All right? And so the notion of Skype is it's for people. All right? It runs on your silly machine. I mean, my wife has a friend in Maine she plays Scrabble with. And, you know, they use a Scrabble site and they use Skype. All right? Been doing this for a long time. And, you know, if everybody uses this from their laptop for goofing off with their friends, if the quality isn't so great, it doesn't matter. Let me say, there are a couple other things that Skype depends on. It depends on reasonable broadband to the home, and it depends on over-provisioning of the backbone. Right? That is, we've not done a very good job of delivering quality of service over the internet, but excess capacity, over-provisioning can compensate for lousy quality of service, or rather, can compensate for your inability to implement quality of service, which says this is a voice connection, so it needs to get its packets on a regular basis. All right? If I have sort of profligate capacity, right, then my inability to precisely get this capacity to the right place at the right time doesn't matter so much. Right? And so it seems to me then what these guys did off of their previous peer-to-peer file sharing exercise would say, hey, we understand peer-to-peer, and voice over IP for consumers, for individuals, is ready for prime time. It's pretty clear that this notion of hooking people up in peer-to-peer networks so that they discover each other and connect directly to each other works. Everyone's comfortable with Friendster and building these social networks and things like that. Let's put this together. I don't know what the status is of actually monetizing this. I haven't read the articles in the paper today, but my sense is it's not so great. But I think this is just, it's a worthwhile exercise to think about where the components came from, why the time was right, and what's the secret sauce that allowed them to do this so quickly and have such a broad penetration so fast. This is from a study done a few years ago by the Milken Institute. And what they try to do is look at policy factors, that's in the left-hand column, and their importance during the inception, growth, and sustenance or fortification of tech businesses. And you get 0 to 3 stars. Okay? And the ones that get the most stars across the board are research institution, quality of labor force, and housing, zoning, and quality of life. Okay? So, for example, tax incentives are great for attracting companies. Okay? Oregon spent tons of money attracting electronics manufacturing to the state 20 years ago. All right? At the same time, that was money that could have been spent to shore up their higher education system and their K-12 system, but instead it wasn't. So they have no mechanism for sustaining those companies. Tax incentives cause companies to arrive. They don't typically cause companies to stay. They're not the big factor. All right? The big factor is things like the research environment, the intellectual environment, and the workforce. Okay? So, you know, in this region and in your region, there are tons of research institutions. Okay? Most of them industrial or federal. For example, the Pacific Northwest National Labs in the eastern part of this state. We've got Boeing, Seattle Biomedical Research Institute, the Hutch. There's a small Intel lab here and adjacent to Berkeley and Carnegie Mellon and Cambridge. There's the University of Washington, of course. There's Microsoft Research, which has 700 people worldwide. And still, the correlation between successful economic development and successful research universities is incredibly high across the country. And there are a bunch of reasons for that. You know, the most important one, and I try and keep emphasizing this, is the students we produce. right? You know, you're producing well-educated people who create companies and staff companies, and there are a set of other reasons. And, you know, I think the fact that universities are open and a neutral meeting ground is a strength that's often underestimated. In computer science, there is a question of sort of what our research is like. And for those of you who haven't read this book, it's sort of a one-chart book called Pasteurs Quadrant. And what it does is to argue that the traditional view of fundamental research and applied research being on a continuum is wrong, that you need to take a two-dimensional view of it, concern with use and concern with fundamentals. Now, the bad news is that most work is in the lower left. You know, it's not very fundamental and nobody's going to use it. Okay? So in some sense, the challenge is not necessarily to get to the upper right. I don't want to argue that that's goodness. It's just to get yourself out of the lower left. All right? So physicists tend to be in the lower right. Okay? The concern is for fundamentals and less with use. A guy like Edison, and again, these are examples from the book, is in the upper left. Not so much of a concern with fundamentals, but a huge concern with practicality and use. And much of biomedical research and information technology research is in the upper right. Okay? It's fundamental, it's long-range research, but you're trying to solve a problem, right? So it's well motivated from an application point of view. Now, another issue for information technology research is what's the role of industry? And this is something that we have to keep explaining to every new Congress, and it's a little complicated. Industry R&D is largely focused on engineering the next generation of a product. And that's a really hard job. If it were easier, we would have more successful IT companies, right? So it's a hugely hard job to engineer products that people are willing to pay money for. This is very, very difficult. Microsoft's investment in Microsoft Research is worth talking about, but it's almost unique among modern IT companies, right? And you know, 30 years ago, the IT pie in this country was a lot smaller, but a big proportion of that pie was IBM and Xerox and AT&T, and each of them had a significant research operation. Today, the pie is enormously larger, thousands and thousands of successful companies, and Microsoft stands almost alone, Microsoft and Intel really, among modern IT companies in investing any significant amount that looks more than 18 months out. Okay? So, you know, Dell, nothing. Oracle, nothing. Cisco, our phrase for Cisco is their R&D became M&A about 10 years ago. All right? And that's not bad. Okay? It's a successful company, but what it means is that they're not looking for what are going to be sort of the transformative innovations. They're going to create entirely new categories 10 years out. Microsoft began this investment in 1991 when it was a tiny little company. Right? So how much of Microsoft's $7 billion in R&D is looking more than one product cycle out? Now, you know, the number may not be $7 billion anymore because they've changed how they count stock and options and things like that. But this is, and also there is work in the product groups that looks more than one product cycle out. But the first approximation, think of Microsoft Research as being the part of Microsoft that's looking 5 years out or more. Okay? And Microsoft doesn't report the expenditures on Microsoft Research, but it's about 700 heads. Okay? And so you can figure out that it's a couple $100 million, and that's real money. The entire National Science Foundation investment in IT research is on the order of several $100 million. All right? But on the other hand, it's a pretty small percentage of a $7 billion R&D budget. And I don't mean this as a criticism. They, in fact, deserve enormous credit for being one of the few companies that's investing anything looking more than one product cycle out. All right? But the vast majority of the R&D investment is engineering the next product. Why might companies be reluctant to invest in R&D that looks more than one cycle out? You know, again, this is a book that I'm sure all of you have read since this is a largely a business audience, okay? And, you know, I think it's a $0 billion market problem. All right? And the fact that if you're going to invest in R&D that looks more than one product cycle out, you have to believe that there is a fairly large chance that you're going to be the company that manages to appropriate that, to turn it into successful products. And in fact, the track record of major companies turning their own innovations into new product categories is not very good, precisely because of the innovator's dilemma. All right? If you're a big public company, you can't afford to be putting a lot of effort into a $0 billion business, right? Because it's not going to be growing the bottom line in the short time. Okay? So this nation has an infrastructure. And some of that infrastructure is physical, and some of that infrastructure is intellectual. And when you fail to invest in that infrastructure, right, you don't see the results of that lack of investment in 1 year or 2 years or 5 years or often even 10 years, but eventually it comes to bite you. I won't tell you what my wife and I had to spend putting the deck back on our house this summer after 20 years of ignoring it, okay? And so I think the intellectual infrastructure of this nation is in a pretty serious state of disrepair due to lack of investment, and it's headed the wrong direction. All right, this is the educational infrastructure and the research infrastructure. And as citizens, you know, everybody wants to be an entrepreneur. But ultimately, if you're going to be able to create companies, there got to be ideas that you can assemble into the products that are going to become the basis of those companies. So obviously, there are important business innovations involved. There are also technological innovations, and the magic is putting those things together, putting the business innovations together with the technological innovations. And you've got to have the investment in the intellectual infrastructure if you're going to be able to do that. And that's an issue for the nation as a whole. That's all I had to say. Thanks for your time.